Yeah, that's a little space, sorry.
No, but the problem is,
I think
I think it's good like this.
I need to take care of the time. What about the time?
Okay, my name is Tarmo. Uustalu. This is joint work with Silvio Capobianco, and it's about something different for this session. It's about cellular automata and graded monads. So monads and grading are the connection perhaps to programming languages. So what's it about? So cellular automata, such as Conway's famous game of life, they are, if you wish, an archetypical example of a notion of computation that isn't monadic in the sense of all these effectful notions of computation like non-determinism or state or exceptions or whatnot. But it's comonadic. What do I mean by this? Well, when we say we're dealing with a monadic notion of computation, the idea is typically computation in some sense happens in the Kleisli category of a monad. Here, the dual thing happens. So the computation happens in the coKleisli category of a comonad. So we all know in the Kleisli case, the situation is somehow like we say by the type that some type of input is taken into some type of output. In the Kleisli case, actually the output is a bit more than the purported type, right? I mean, if an exceptional computation is supposed to take you from A to B, it really takes you from A to something else than B, 1 plus B. Yeah? There is the possibility of an exception. In the case of comonadic computations, you take input to output, but what you actually use as input is a bit more than you purport in the type. So that's somehow the game. Okay. So two things will happen today. I want to tell you that you can also see cellular automata as graded comonadic, and that's nice for two reasons. One is that it's in some sense more precise. It takes you to kind of a resource-aware world of a cellular automata computation. But another is it takes you into a more basic setting, and I'll tell you exactly in what sense that is. And then I also want to talk about additive cellular automata, which is just a special class of cellular automata. I'll tell you what they are. But the fun thing is they turn out to be both graded comonadic and graded monadic at the same time. So they have this sort of dual nature. They don't know what they are. And this is actually explainable by something from category theory. So there is a theorem about adjoint comonad and monad pairs that we generalized. It was an easy generalization to the graded case, and it actually falls out from there. And some very basic initial observation. So that's it. So cellular automata as comonadic, I'll briefly review this. Then I'll talk to you about this paper's contribution, that cellular automata graded comonadic. I have to explain a bit about graded comonads and the graded Kleisli, graded Kohlenberg-Moore, but on a shallow level because it's late and I don't have a lot of time. And I'll tell you what additive cellular automata are, and I'll tell you this story about that you can see them as both a graded comonadic, but also as a graded monadic notion of computation. So here is a cellular automata, a famous one. So I use this to explain the basic ideas. So what is cellular automata computation? You work with some sort of an alphabet, first of all. So here the alphabet is just Booleans, or white and black on the picture. And then synchronous computation happens on a heterogeneous grid. Here the grid is just integers, so the integer axis from the left to the right. There is another axis, this is time, so that flows from the top to the bottom. So the thing in the first row is a configuration. It's an assignment of letters to every node in the grid. And this is a next configuration to which we get, applying the cellular automaton to the first configuration, we get then to the next, and then we can iterate the automaton and we get this nice picture. And what happens everywhere, at whichever configuration you are, maybe you're here, you want to know maybe what the letter is going to be here, like here. It depends on what is in the previous row, what is in the input configuration, not necessarily at the same node, not necessarily immediately above, but also you may use some information from the neighbors. So here, the neighborhood is actually your own node and your immediate left neighbor, your immediate right neighbor. So if you look at this thing here, it conforms to a certain pattern. So white, where am I now? Did I jump? White, black, black, which is this thing here. And here the rule says if you see white, black, black, the color will be black, right? Okay, so what is a cellular automata? there are these two ingredients as parameters. There is a monoid, which is for the grid. You think of the unit as the origin, and the multiplication as something that tells you how you can shift around. And then there are two sets, x and y, which you think of as the input and output alphabets. If you want to iterate a cellular automata, the input and output alphabets better be the same. But in general, there is no need for them to be the same. I don't also require that they're finite. I don't require that the grid is a group, which people usually do in cellular automata theory. And then what actually specifies the dynamics is a local rule, which is a function like this. So you go from x to the power of g to y. So you work out a single output letter from an input configuration, which is an assignment of input letters to nodes, right? So to work out a single letter, which by convention is always the output letter at the origin, we can use the whole input configuration, but actually you should only depend on a finite part of it. And how much finite shouldn't depend on the actual configuration. It should really be a constant sort of modulus of continuity, if you wish. So that's the game of a local rule. So rule 30 has this as the data. So integers are the grid, booleans are the alphabets, and the local rule takes a configuration. It only uses the configuration at 3 points, -1, 0, and 1, and it gives you what the output value will be at 0. Well, 0 is the unit of integers and addition, but generally we use multiplicative notation. Alternatively, you can specify a global rule which tells you at once how to get from an input configuration to an output configuration. That is also subject to conditions. It has to be uniformly continuous, namely there has to be a fixed neighborhood on which you can depend, namely to work out the output at node n, you can only depend on the sort of n times m part of the input configuration. So the original neighborhood shifted by n. And you have to commute with translations. It shouldn't matter whether you shift your translation, apply the global rule, or apply the global rule, shift the translation. This somehow captures the idea that the same thing happens everywhere. The rule is not different at different places. There's a classic theorem about cellular automata that local and global rules are in bijection. So to get from a global rule to local is very easy. You just apply the global rule to one particular node of interest, namely the origin. In the other direction, you just translate the configuration by the amount given by your node and apply the local rule. So you pretend that the origin has moved somewhere. So this is a perfect comonadic notion of computation, as Dan Pipponi noticed, and we also noticed in 2010. And what you can use is the co-writer comonad. The comonad takes a set X, an alphabet, and gives you basically the set of configurations. That's the base functor of it. And the co-unit is something that from a configuration extracts a single letter. So this just applies the configuration to the origin or to the unit of the monoid. And co-multiplication is a thing that takes a configuration and blows it up into a configuration whose letters are no longer the original letters, but they are whole configurations, which is kind of the local view of the configuration, like I'm pretending that I'm the origin. Okay. And ignoring the requirements of uniform continuity, local rules are exactly the same thing as coKleisli maps for this comonad, and global rules happen to be exactly the same thing as co-free coalgebra maps of this comonad. And it's kind of a standard thing that the coKleisli category is a full subcategory of the Coallenberg-Moore category given by exactly the co-free coalgebras, and then of course the maps between them. And then this Curtis-Hedlund theorem, for example, is just an instance of this isomorphism for any comonad, not only this one, of the coKleisli category, and then the full subcategory of the Coallenberg-Moore given by just only the co-free coalgebras. Okay. But I cheated, right? I ignored the uniform continuity. So you have to put it back. One way to do it super cheaply is to switch from set to the right category, where your only notion of maps are the uniformly continuous maps. So one place for that could be like metric spaces, but here we can go more abstract. You could do it with uniform spaces. And I don't want to go into any detail of this, but it's something between metric spaces, where you can speak about uniform continuity and topological spaces where in general you cannot, right? But you can talk about uniform continuity without the metric. Okay. In this paper, alternatively, why don't we just try to stay in set, but take the neighborhood, so this uniform continuity modulus, the subset of the monoid that you treat as the neighborhood as part of the data. So then you're kind of resource specific. Then you always know when you talk about cellular automaton how wide a window the cellular automaton actually uses. Okay. Graded comonads, what are they? Well, they've entered the PL community again in the dual form, right? So people use graded monads, especially like Paul-André Méliès and Shinya Katsumata, and now a whole lot of people. It's kind of also a way to do static analysis, maybe sort of explained category theoretically. So type and defect systems are recast in terms of graded monads. Graded comonads are just a dual. So we'll do graded comonads on set. So you need to start with a pre-ordered monoid. So a monoid whose multiplication is monotone in both arguments with respect to some pre-order. And what you want, instead of one functor taking sets to sets, now you have a whole family. For every monoid element, for every grade, you get one such. And this is natural with regard to the, this is functorial with regard to the pre-order. And also you have the co-unit and the co-multiplication, but the co-unit is the thing that is only uses the functor at 1, the unit of the monoid, and in the case of co-multiplication, you somehow split resources, right? This is what is happening. Otherwise, it looks very much like ordinary comonads. Now, cellular automata graded comonadic for which monoid? Not the grid as the monoid, because it doesn't have any order, but the monoid given by subsets of the given monoid. So it's like going from words to languages, for example, right? So the carrier are all subsets, finite subsets. The order is the converse of inclusion, sorry. The unit is just a singleton set consisting of the origin, and n times m are like all small n times small m from capital N and m. Capital N and m are neighborhoods then. So we grade by neighborhoods, and then there is this graded co-writer comonad that just keeps track of how much is used. So dmx is not x to the power of g, not x to the power of the whole given monoid, the grid, but just the neighborhood. If m is smaller than or equal to m prime, which actually means m prime is contained in m, then you can restrict the partial configuration over m to a partial configuration over m prime. So that's your functoriality. The co-unit only needs a neighborhood consisting of exactly one element, because to pick out one letter, you only need one letter. And some kind of arithmetic also happens in this explosion case, all right? And then there is like a graded version of translation that you can work with. So what are the coKleisli and co-free coalgebra maps of this D-like? Well, they should be some sort of nice maps that we can compose, and composition of these local and global rules should work exactly the same way as coKleisli and co-Ellenberg-Moore composition. But the fun thing is, when you do the coKleisli and co-Ellenberg-Moore constructions for graded comonads, these won't even give you categories. They give you something called locally graded categories. So you don't even get, you don't really get maps. You get something called, that we should call graded maps. So now I have to show you 2 slides about locally graded category theory. This is very old and goes back to Richard Wood's PhD thesis in Canada in 1976. You also start with a, they should say, pre-ordered monoid. And it looks like an ordinary definition of category. You've got a set of objects, you've got a set of maps, you've got your identities and composition, except instead of one single family of maps from X to Y, actually, one single set of maps from X to Y, you have a whole family. So for every grade, you have a set of maps. Maps are graded. Maps are sorted by grades. And composition and identities are somehow about these grades. Namely, identities, they're always of grade unit. And when you compose 2 maps, their grades get multiplied in the monoid that you use for grading. So in our case, neighborhoods. And also, you can upgrade maps. So if m prime is smaller than m, then if you've got a map from x to y of grade m prime, then you can upgrade it into one from x to y. And then there are some very sensible laws, which I cannot go into. I mean, the usual category things. There is something that says that upgrading twice is just one bigger upgrade. And there is an interchange law between composition and upgrading. Okay. coKleisli looks exactly like what we want. So if you've got an m-graded comonad, the locally graded category, which is its coKleisli category, will be not m-graded, but m-oprev graded, which means you have to take the converse of the partial pre-order, and you have to swap the arguments of the monoid multiplication. So that's what m-oprev is. It's just a modified monoid. And then a great thing is, the objects are just the objects of the base category, like in ordinary case, in our case sets, but a map of grade m from x to y is exactly something like this, which already looks very much like our case, right? So there are not just, ungraded maps, but we can only talk about maps within a given grade. Okay. Then you can upgrade maps, it works perfectly, and composition really plays this game about neighborhoods. Coellenberg-Moore is also something, here I cannot go into any detail, but the coalgebra will actually not be just a set, but it will be a functor from the monoid to sets. And the carrier is not a single, the structure map is not a single map, but a family of maps, but the laws are exactly like the normal ones for coalgebras and the same for coalgebra homomorphisms. The important thing is again that the Coellenberg-Moore locally graded categories m-oprev graded. There are maps of grade m, which on the level of carriers exactly will go from like dmx to dmy, which is what we want. And also you maintain the old thing that the coKleisli category is isomorphic to the full subcategory of the Coellenberg-Moore category given by co-free coalgebra. So the classic theory carries over to this locally graded setting. That's the point. And then you can then there is a graded comonad, as we already saw. This is just to repeat what I already showed to you. The cool thing is if you look at the terms that define the data, they are exactly the same as for the ungraded case, except that the types are more precise. We just see what neighborhoods we're using. Now, the coKleisli maps of grade m of D are like this, which is perfect. And they compose like the cellular automata do compose, like the local rules compose. The co-free coalgebra maps of grade m, they are a bit more interesting. They are families of functions. They are indexed by a neighborhood, so you've got a bunch of functions. Fn will have this type, which basically says, if you want to see n many letters on the output side, it will tell you how many you need on the input side, what is in the neighborhood there. And it will actually be, if the neighborhood of the automaton is m, then it will be actually m shifted by n, so it will be n times m. And this is how and they're subject to some conditions, but they precisely correspond to uniform continuity and naturality, and to just commuting with translations. So these are exactly the local and global rules, but in a resource-aware form. So we somehow went from kind of simply typed cellular automata into cellular automata where there is more type information, so you always know precisely how much neighborhood is needed for anything. Okay. Additive cellular automata is the last thing I want to say. So this is a special case where your alphabets have some structure. So you want the alphabets be commutative monoids. So for the grid, I used multiplicative notation for monoids. Even if my example was kind of additive, it was integers with addition. But for these alphabets, I really want to use addition, and that's what people traditionally do. So you just assume that the alphabets have some commutative monoidal structure. And a local rule is like before. It takes a whole configuration and it gives you one single letter, which is the output letter at the origin, and you can find the output anywhere else by just shifting the configuration, which corresponds to multiplying in the grid monoid. But now there is a restriction that the local rule has to be additive. And this is just a word that means it has to be a commutative monoid homomorphism, which means to say it has to preserve addition. So that is all there is. Now, clearly you can see these things as comonadic and graded comonadic. How? Well, you just have to go to the right place. So if I want to see them as comonadic, then uniform spaces won't do. I need uniform commutative monoids, and everything will be just great, kind of automatically. If I want to do graded, I could just work not with a graded co-writer comonad on sets, but with a graded co-writer comonad on commutative monoids. But that's boring. I want to say a bit more, right? So let's work a bit with this graded co-writer comonad on commutative monoids. I want to say there is some magic that says there will also be a monad on commutative monoids that will also do a thing. A monad on commutative monoids that will also explain this notion of computation. So what's the observation? The observation about additive local rules is that they are fully determined on what they do on relevant point configurations. Why? Well, what is a point configuration? A point configuration is basically a configuration that is 0 everywhere except at one point where it can have some value of interest. And I have a 0 around because my alphabet has this algebraic structure of an additive monoid, so there is a 0. So the point configurations are just this. So for any point, if the point is the one of interest, then there is some value, otherwise 0. And if your local function is additive, then whatever partial configuration over M you're given, you can just cut it down into a sum of point configurations over that neighborhood, right? Like this. And then K has to preserve this big multiplication here, and you can see that all I need to know is what K does on point configurations. But that means that these additive functions from x to the power of m to y that take a partial configuration into a single letter are in bijection with these local rules, or with additive functions I should say, that just take a single letter, they take a single node, and then they'll give you an output letter. And this is what? This is for a given node, if I put in the input a value from x there, what I get to know is that the contribution of that letter to the whole letter that will be at the origin on the output side. So every letter in the input that is in the neighborhood makes a contribution in terms of a share, and I can just think of just these contributions of individual letters at individual nodes determining the whole behavior. So therefore you get that additive functions like this are in bijection with additive functions like this. Well, this one perhaps is a monad. This is a good candidate for a Kleisli map of a monad, right? Or maybe a graded Kleisli map of a graded monad, really. And this is where I'll get. So it turns out that this functor dm is self-adjoint with itself, but I will give it another name t as well because I want to treat it as a monad. And it's just this exponentiation thing, right? And there is a bijection between maps like this. Now, so here is an example of it. 5 minutes. That's more than I need. Okay, here is an example of this. I can go slower now. So let's look at the grid again, just to give you an example of an additive cellular automaton. So here's a grid again. The grid is again integers, right? With actually addition as multiplication, so to say, the monoid multiplication. My input and output alphabet are equal, and they are just rationals, and also with the additive structure. So since the input and output are the same, I can run this automaton many times and kind of show a diagram like before. So I could maybe start from here and get to these places where my dynamics is this. This time, the neighborhood is just 2 nodes. To get a letter at any node, I just need a letter at the corresponding node in the input plus the left neighbor. And this function preserves addition because it's a linear thingy. Right. So here it's written as a coKleisli map. So saying how from a configuration, of which I only actually need to know 2 points, what the configuration is at -1 and 0, give me the output letter at the origin, which is, well, here in this picture, right? So for example, from these 2 values, I'll get this 2/3, or from these 2, I get the 1/3. What is this other format? What's that guy? So here I said what it should be. It should be for any input letter, the contribution it would make if it was placed at a certain node. And the contribution it would make to the output letter at the origin. Where am I? I'm going in the wrong direction. So this guy is here given like this. If the letter is X, and if it's put at -1, then the contribution it makes is this guy, which you can actually kind of read off from here. If the letter is X, and if it's placed at node 0, which is the origin, then the contribution it makes is this. So here is these 2 different formats, and you can go from one to the other. But only in this additive case, it really uses that 0 is preserved and binary addition is preserved. Therefore, all finite additions are preserved. Okay, here's an old thing, and we've tried to find a reference. Curious is that the dual result was proved by Allenberg and Moore, I think, in '64. But this one, about Kleisli and coKleisli categories, maybe only by Kleiner in 1990. Given 2 functors, D and T on a category, such that they're adjoint, the following happens to be true. If D is a comonad, you automatically get a monad on T, just from the adjunction. If T is a monad, you automatically get a comonad on D, just from the adjunction. Moreover, the unit and the co-unit and the multiplication and the co-multiplication will be in a special relation that's called adjoint natural transformations, or mates in some terminology. So this is really canonical. And actually, these 2 constructions, this and this, give you a bijection between adjoint comonad structures on D and monad structures on T. So if D, for example, happened to have 5 comonad structures, T will also have 5. Yeah, if D didn't have any, well, T won't have any. What is more, for the corresponding comonad structures on D and monad structures on T, the corresponding coKleisli and Kleisli category are actually isomorphic. Moreover, on objects, the isomorphism is identity, and on maps, it's precisely the bijection between maps like this and maps like this, which is provided by the transposes of the adjunction. So this is very, very cool. Turns out you can do exactly the same for graded comonad-monad pairs. So if you're given, now you need to a pre-ordered monoid to start from, right? So if you get 2 assignments that just for any monoid element give you an endofunctor, so it's 2 families, dm and tm for every m, then what happens? If D carries an m-graded comonad structure, then T carries a right adjoint m-oprev graded monad structure, and if T carries an m-oprev graded monad structure, then D carries a left adjoint m-graded comonad structure. And M and M-oprev have the same underlying monoid. It's just that the pre-order is reversed, and the multiplication order is reversed. And also, the functoriality, this bit, comes automatically. So if you knew this guy, you will know this one, or the other way around, and here also. And these are in these adjoint relations. And you do get a bijection between these structures, and moreover, you get that for a corresponding graded comonad and monad structures on D and T, these locally graded M-oprev graded categories, coKleisli and Kleisli, are isomorphic. So this all just falls out completely, generally, in any case, not just for our case. This is my one but the last slide. Additive Cellular Automata Graded-Monadic. Remember, we already have an a junction like this, where dm and tm are actually the same functor, but I just giving them different names because I want to think of one of them as acquiring a monad structure, the other one has a comonad structure, a graded comonad structure. We already know D carries an M graded comonad structure, therefore automatically T carries an M oprev graded monad structure, and you can work it out. Too late to go into this, but for example, this thing that allows you to change the grade of a thing, right? So if you know that M prime is greater than M, I should be able to go from data like this to data like this. Previously, I was able to shrink partial configurations. Now I would need to go in the opposite direction to extend them. That's actually impossible in the general case, but now I've got 0 around, so I can just pad out with zeros whatever is missing. So if I go from a smaller neighborhood, I've got a configuration over a smaller neighborhood who want to have one over a bigger one, I just fill it out with zeros. And then Kleisli maps of grade M are precisely in bijection with these coKleisli maps of grade M, which already we knew were the resource-aware forms of local rules. So you can see the local rules also as Kleisli maps. The situation about free algebra maps, you can also interpret them, but that's a bit more complicated. It turns out the monad is known. It's actually known as the monad of formal polynomials. So that's the right thing to use in the case of additive cellular automata. If you want to treat them as graded monadic, that's explained in the paper. So the monad structure has something to do with substituting polynomials into each other and getting new polynomials. Takeaway, cellular automata are a nice example of a comonadic notion of computation, but they exemplify more. It's natural to consider grading. It's actually great to consider grading in this example. I think they are actually a good example. Here I had to run very fast, but the definitions of locally graded coKleisli and Kohlenberg-Moore construction are complicated and involved, and I think this is one of the best examples if you work it out that gives you some intuition why the definitions even are like this, because here you can clearly think of like which regions do I need to use of the configuration. Yes, and then additive CA are among the rare examples of notions of computation that happen to be both comonadic and monadic at the same time. Thank you.
Quick question.
Yes.
How common is this?
I'm sorry, could you repeat the question to the microphone?
Yes. How common is this situation of having comonad and monad pairs? Which is quite nice. I was looking for that a long time.
It is actually rare, as I say here.
Yeah.
So maybe some examples that we typically know is something like, you take the reader monad and the co-writer comonad and they're adjoint, right? Or you take the writer monad and the co-reader comonad, they are adjoint. And there is this result where you have a comonad on the right and comonad on the left, monad on the right, gives you isomorphic Kleisli categories. There is a dual result, that's the older one, where you have a monad as the left adjoint, comonad as the right adjoint. Then you don't get that the Kleisli and coKleisli categories are isomorphic, but you do get that the Allenberg-Moore and co-Allenberg-Moore categories are isomorphic. So it's kind of a nice story that happens there that is kind of relatively little known in computer science. But also, I think, for lack of examples, really. It's not very relevant, because these examples are rare.
So have the coffee break. So
Yeah, sure.
Thank you very much.
Thank you.